Okay, what if we have what we call a diffraction grating? What a diffraction grating is just a large number of slits that are separated by a distance d, by the same distance d. Usually the way the gratings are labeled, like 500 lines per millimeter, meaning that we have 500 slits in every millimeter, sorry. Now, to get D in that case, we need to divide the 1 millimeter by the number 500. That would be our D, the separation of the slits. Now, when we have a huge number of slits, like when we have 2 slits or three slits, it does not matter how many, the equation that gives the position of the principal maxima is d sine theta is equal to n lambda. However, as the number of slits increase, the principal maxima are going to become very narrow. Now, for example, 500 slits per millimeters is going to give us very, very narrow slits. Very, very narrow fringes, principal fringes. They are going to be very narrow and very bright. Their brightness is going to be proportional to the square of the number of slits involved. Now, another thing is the secondary maxima are going to be too dim to be observed. We are not going to be able to see anymore the secondary maxima. In a diffraction grating, when the number of slits is huge, the secondary maxima are not going to be visible anymore. How would the grating look like? Usually, like the one we'll have in lab, it's going to look like a slide like this with a piece of plastic on it. So these are different gratings. This is from a website that sells gratings. This one here from a university website, this one and this one, they are both from the same university website, and they are being used to view some spectral lamps. This is, I believe, is a hydrogen lamp, and this is a helium lamp. And this is also, this is not showing us the grating, but it's showing us the light coming out of the grating, and also looking at a spectrum lamp. And I believe it's still again a helium spectrum lamp. Now, this is quite interesting. Actually, what we have here, a green laser beam that's shining on a grating. So you have the central maximum there, but then what you have, you see the very thin beams all the way around in the other directions. When commonly available grating to all of us is a CD or a DVD player, since the way CDs work is by having small notches in the plastic there. That's the way we listen to music, so it's a piece of plastic with multiple holes in it. The holes are going to count as 0 or 1 if they exist. It's a 1 if they don't exist, it's a 0, and that's the way the music is recorded digitally. Now these holes are going to act as a grating or multiple slit interference, and that's why we are seeing the rainbow through that CD. Now, I mentioned earlier you can use a grating to look at spectrum lamps. Now, elements are going to emit light depending on their makeup, their atomic makeup. And actually, the spectrum of the light that comes out of each of the elements is a sort of a fingerprint of that element. That's the way we know the structure the atomic structure of each of the elements is through the light that they emit. For example, here, I got it from this website here, we have for hydrogen, this what looks like the spectrum, the spectra that we are going to see. This is for helium, lithium, and so on. Now, a grating works very well in separating light colors, because if we go back to this screen, the central maximum is going to be the sum of all colors. But then the blue light is going to have its maximum closer to the central maximum. Because remember, delta Y is lambda L over D. So lambda is a smaller lambda for blue light. So this, the fringe separation is going to be smaller than for red. That's why we see the maximum of the blue here and the maximum of the red further out here. So this is delta Y for the red is from here to here. Delta Y for the blue is from here to here. Now, the next red is going to be here, the next blue is going to be here, and you get the additions here that's not going to show you the different colors. Now, if I have a grating, meaning I have more slits, the more slits I have, the narrower these fringes are going to be, and the more separate I'm going to be able to see them. If the blue one is not as thick as here, we are going to be able to distinguish it much easier. This is here white light, so we are seeing all colors. So if we have a spectrum lamp where we have just definite colors of light, we are going to be able to see them more distinctly. So the central maximum is still going to be white, but then here I'm going to have the maxima of the different color at different locations. And that's essentially the principle of a spectrometer that a lot of you have used in chemistry or sometimes in biology. That's what we are having here. So that's essentially what we are doing. We are looking at the different colors. Here is my white, my central maximum, and here it's not really white, it's the sum of these colors, whatever they are. And if I have spectra lamps for each one of these elements, we see those light beams when we view them with a grating. Okay. Now, before going on, I'm going to go to WebTop again and play with the gratings simulation. Now, here is the grating that looks very much like the slide that we talked about, and we are shining light on it from this side. And if we are going to look in the other side, this is what we see. And this is the central maximum for this particular light beam. And you notice here it's somewhat yellowish. That's a helium light bulb. It's the helium spectrum. So that's why helium light bulbs, you see them somewhat yellowish. And that yellowish is the sum of these colors that we see here. A little blue, a little green, a little orangish, and a little red. These are the different spectrum lines for helium. Okay, I can try to see them more neatly by increasing the intensity here, like overexposing the film of our spectrometer. Now the wavelengths are shown here. 438, 447, and so on. If we look at a hydrogen lamp, it's going to look slightly different. So it looks a little bit reddish in the middle, and you see the different light beams are going to be these. Okay, the red is the most prominent, and that's why the overall is somewhat that color. If we look at a mercury light bulb, it's bluish. That's why in the street, when you look at mercury light bulbs, they are more of a bluish tint. You see there the sum of all colors. You have blue, green, and red. And sodium light bulb is more in the yellow. It actually does not have much else, just two wavelengths in the yellow. Now, in addition to gratings, the same principle of interference is actually the way we look at matter through X-ray diffraction. To be able to figure out the structure of crystals, what we do usually is we shine X-rays on it, and we kind of look at the reflected X-rays. And what's going to happen is the X-ray beams reflected off the top are going to interfere with the X-ray beams that are going to be reflected off the other layers. Now the path difference is going to be twice d sine theta. Now when twice d sine theta is equal to m lambda, that's going to give us the positions for constructive interference.